Thank you, everybody, for being here today, and thank you also, Giacomo, for kindly accepting the invitation. Today, Giacomo will talk us about existence and follow-up for non-autonomous conservation laws with viscosity. Thank you, Giacomo.
Thank you, Davide. Thank you, the organizer. Thank you also the audience to be here. There is a work about a recent work together with Stefano Bianchini. Is about the following PDs. Maybe I can write on the paper so that we will have sorry, the blackboard, so you can see even if I change slide. So it's a parabolic. It's a parabolic PDs in this kind. Equal to x with the initial datum and 0 such that it's positive in L1 and L infinity. We will study these PDs in the two following cases: if P belonging to a P or Px belonging to a P. There are other conditions here, but the condition here are just to ensure local existence of the solution and utility from initial data. The PD is in time space R. So this is a one-dimensional problem in space. So maybe one of the most classical example of application of this kind of PDs is the pollutant on the river. So we have a river with some shape, you have some pollutant, which is naturally spreading around due to the thick effect. So there is a dissipative term. There is the second derivative called the Laplacian. And then there is a drift term, which depends on the shape of the river. So in this case, this is the drift. Okay. Since we are talking about the pollutant, maybe you want to find a solution such that a certain time is concentrated in only one point, unless you want to spoil the plant, of course. So you look for initial data such that there is a time t, which that you convert into a delta at time t. For our formulation of the problem, we will do something slightly different, but in the end will be equivalent for this kind of PDs. So we are looking for blow up in L infinity norm. Means look for initial data such that there is a fine tuning such that the L infinity norm blow up at time t. So, of course, there are other models where you want to avoid the blow up. For instance, if you want to spread a drug on a field, you want to kind of spread the drug everywhere. So in this case, you will look for a solution that does not blow up at final time. We'll call let's say this kind of the opposite condition global existence for the solution. So okay, here are a couple of 3 remarks about the PDs. They are quite standard. So by normal formula, these kind of PDs with the condition I gave before is locally well posed. indeed you can find the solution as the contraction of this operator in a suitable spaces for the two conditional cases we are studying. So second, the solution is positive at every time because of the comparison principle which holds for these kind of problems. And if you consider the mass, which is the L1 integral of your function, this is constant in time. It's also came from the PDEs. And in particular, unless to rescale your solution, you can always assume that the mass is equal to 1. So you're working of a probability if you want. So the question, you want to achieve the following. You fix K and P. And you wonder when for such K and P, for every initial data, there is global resistance. So you find the global resistance condition. So I will talk about 3 papers. In the first paper, it's a paper of Guidolin, Schultz, Dibel, and Ligano. I hope I pronounced well these names. They studied the case where B is flip sheets, but one can generalize to the case of K, which is called subcritical case. So critically is defined as 1 minus 1 over P if B belongs to LP, and 2 minus 1 over P if Bx is belonging to LP. So if K is subcritical, then there is global resistance. This is the result of the first paper. And there is another paper I will talk about in Toscani, where he provided a method that we use to prove that for supercritical, in the supercritical case, there are a sample of blowout at time. In particular, the solution is convergent to a delta, so you have block for every LP norm with P bigger than 2. You don't even have AP integrability for these kind of solutions. And then for critical P, for the critical case, in our paper together with Bianchini, we proved the global resistance. So first, I forgot about say that actually there are in the paper of Bianchini we work with slightly general more spaces. They are weak spaces LP. But for the topic, we don't really care about there are some technical complications, but we can pretend we are working with a LP norm. Just to say that actually there are some we achieved in the paper. It's slightly more general than this. So there are, of course, many other examples of nonlinear conservation law with viscosity. I want to give just a couple of examples. First one is Burger equation, very classical equation introduced by Burger to generalize an Aristotle equation. The second equation came from a model of hierarchy sparati, which is actually the PDEs that Toscani taken in his paper. And what they prove is what they wrote in a couple of papers where the first that with dimension 1 and then with multi-dimension, they introduced these PDEs, which is a nonlinear Fokker-Planck equation, where the drift it has this nonlinear term in order to try to describe a gas of bosons of Ferners. And in the paper of Toscani, right here.
I don't think anyone would see at all.
I see. Then I will. in the case of bosons, Toscani consider the energy of the system. Here V is the velocity of the particles and U is the density. So the density depends on the velocity. So the energy of the system can be written as a kind of second moment of your solution Q. Okay, and you prove that the energy in some, there are some solutions such that the energy go to zero at finite time. This means is physically represent the Bose-Einstein condensate. So this is a particular state of matter where the bosons are colliding, are occupying the same quantum space. And this is possible for bosons, but it's not possible for fermions because of the power principle. So there is this kind of physical interpretation of blow-up this for this model. So now I want to talk about these three papers, the three cases: subcritical case, critical case, and supercritical case. Okay, about the subcritical case, the first, okay, we just work with the P belonging to a P. The other case is similar in the idea are the same. They're just a different computation. So the first idea is the following. First idea is the following. Since the mass is finite, actually it's one, you can achieve the density norm as the limit of the n norm with the n going to infinity. In this case, n is an integer, but can also be a real number, possibly a real number. So there are two steps in the proof. In the first step, on a certain interval, fixed interval, you want to estimate the 2n norm with the initial datum and the sup of on the same interval of the n norm. So since you have just the equation, you can write the first idea you can have in mind is taking the derivative of 2n norm. Here there is the power of 2n, just to simplify the computations. You can write, you can use the PDs. In the end, there are two terms. With a bit of work, you can estimate the derivative with the two terms. One is a good term. You can predict. You can think this is came from the dissipation, just trying to push down the mass. The other one came from the drift that may try to collect the mass at one point, providing a block. So we want to study the bad case when the derivative is positive. The derivative is when the derivative is positive, it implies that the first term the certain constant is bounded by the second term. Here you have okay, this is a good, actually, this is a good inequality because we estimate a function, the derivative of a function with the function. So you can use here Galliano-Rierenberg that I call in on the top of the slide. So Galliano-Rierenberg is telling you that you can estimate the LP norm with the LP norm with Q smaller than P, paying the derivative of the LP norm of the derivative of the function. So here you can estimate that you can this condition, which is telling you that the derivative is decreasing. Here you can use Giacomo, and you have again the L norm of the derivative with something plus you have to pick some Q. An idea is, for instance, taking the L norm of UN, so that you achieve again the 2n norm of U. But since we want to estimate the 2n norm with the n norm, they don't write, they don't estimate the Gallagher in this way. They estimate with L1 norm of UN. So then here there are some constellation. Another estimate. And again, this condition is equivalent to the following. You start by UN to the power of norm 2. Use Gallagher 1/3. Yeah, there is a constant, so write it this way. And now from the relation before, you can estimate the derivative of the L2 norm of the derivative with the L norm, basically. With something. So this is the last condition in this condition. Okay, and now if you take the supremum of the 2n norm as a function, or if you want the 2n norm as a function, you realize that there is a level here such that the derivative has to be negative because of the condition we gave. So in the end, if the sup of the interval of the 2n norm is bigger than the sup on the n norm to a certain power, then the 2n norm is decreasing, and the maximum is in time at t0. Otherwise, as well, it cannot cross the sup the sup of the n norm. So this is the first step.
Sorry, Giacomo.
Yes.
But in the Gallagher, you also have a constant in front.
Yes, you also have a constant with I didn't write on the, but this is a universal constant which depends on. Yes, you're right.
In your case, there is a constant that is depending just on n because you have q, which is so p is fixed, which is 2, no?
Yes.
And q is running like.
Yeah, it doesn't depend of
1, 2, okay, and there is theta, but everything is depending on.
Indeed, everything is dependent on n. Indeed, I wrote the sin of n.
Yeah, okay.
But okay, now in the next slide, you want to iterate just to answer to your question. In the next slide, you want to iterate this procedure. So you estimate the L2 norm. The L1 norm is already bounded. The L2 norm with the L4 norm. Sorry, the L4 norm with the L2 norm. The L8 norm with the L4 norm and so on. Or you can start by 2m prime and go to 2m. There are some constants, you're right. But in the end, if you do this procedure, which I'm telling you now, the constant will be universal. Like there will be a limit which is bounded. Okay, and the thing you obtain by reiterating is the following: you can estimate in such an interval, the 2n norm with the 2n norm in the time t0 plus some constant like plus something which depends on 2n norm with m between m prime and n with some constant, some power, and then the last term will be again a constant which now depends on n prime and m sup on the interval of the 2n prime norm. Now you can estimate again the middle terms by using this interpolation equality for LP spaces, and then in the end there will be a constant. Here it depends on M prime again. And max, you can estimate the 2-1 norm with the maximum with just the 2-1 norm at time t0 and 2 M prime norm. Picking M prime equal to 0, so starting by 2, 4, 8, and so on. And sending M to infinity, you're able to estimate the L infinity norm with a constant. Here it will be a universal constant with the dependent M. In the end, there is a bit of computation here, but this is the result. Plus the initial data and the L1 norm. But we know that the L1 norm is constant, maybe equal to 1. So in the end, the L infinity norm is bounded. Okay, this is working only in the subcritical case, because the L1 norm is to a certain power, which I've now run to the black hole. Minus k. If k is converging to the critic case, is go to plus infinity. So there is no way to apply this method for the critical case. I mean, at least there is not an easy way. But you can use the same method starting by instead of starting here, sorry, you estimate 2 with 1, 4 with 2, and so on. You just estimate, you can use this method starting from 2. So you estimate 4 with 2, 8 with 4, and so on. And you're able to estimate the L infinity norm with the initial datum and the L norm. So in the end, it's enough, let's say, to estimate the L norm to have a global resistance for the solution. And this is what we are going to do for the critical case. So critical case start from rescaling. Like rescaling PDs is always a good idea. So fix a time t. You want to rescale first according at time t first in space, and then you will have the middle equation. And then since you want to get rid of this term, the first term, create something. You don't need this anymore. You pick a time tau such that with the following. So in particular, if t is between 0 and the capital T, tau is between 0 and plus infinity. So use this rescaling in time, and you end up with this equation. This is similar to the equation before, but there is an additional term, which will be useful to push down the mass of the solution. In the critical case, B is rescaling by B tilde, but LP norm and the LP norm of the derivative, again, in the critical case, they are the same of LP norm and the derivative of LP norm. So there is good hope that this is a good rescaling in the end. Okay. You want to find some like computation which is similar to the one done in the subcritical case. Instead of estimate the L2 norm and send it to plus infinity, we start by the L2 norm because we have to estimate just the L2 norm. For what I said before. So the derivative of the L2 norm square similar to the before, but there is this additional term due to the rescaling. With a bit of work, you can estimate these 3 terms with other 3 terms, which involve only the L2 norm and the L2 norm of the derivative. So if you forget about the source term, derivative, this is a differential equality for the L2 norm squared. And studying this equation, you realize that if at a certain time tau hat phi of f of the time is negative, then the solution goes as this linearization. So you have a good estimate that in the rescaling, you will have the estimate that you're looking for that norm. So in the end, to prove the critical case, you just need this condition to find a tau such that that norm is small enough in the rescale solution. And so this is our claim, but since you have this estimate, you can estimate that norm with the L3 norm and L1 norm, and you know this is equal to 1. Because rescaling the mass in the end, also the resolution will be the same. And also from the rescale solution, you can realize the mass is still constant in any case. It's enough to prove that the L3 norm of B is frequently small, and indeed the limits go to 0. So this will be the last claim for the critical case. We achieve this claim with another method. So instead of, there is a cutover argument. Instead of considering the B, we consider the minimum between B and A, we call BA. Instead of considering the L2 norm, we consider this function, eta, which is the square of B if the sublevel B is smaller than A. And then it's linear in such a way that eta is C1. So taking instead of the derivative of L2 norm, the derivative of eta, you have the same terms of before, but you replace B with A. So this is good because the last term we can estimate as A to a certain power and L2 norm squared. And if A is small in here, A is a fixed constant, and you pick A such that the last term is smaller in modulus than the middle term. So you can erase these 2 terms, and you can estimate the derivative with the first term. Okay, and now you need to use that we are in dimension 1, because now we are using Galliano-Nirenberg with we want to use Galliano-Nirenberg with the L3 norm. So everything I said before, it's working also in a dimension. You can generalize by fitting the drift, the divergence, and instead of the second derivative, the Laplace. But here you need to use that they are in dimension 1 because Galliano-Nirenberg this form is working on only dimension 1 because of superimposed bending, so classical superimposed bending theory. So you can estimate minus the L2 norm of the derivative with minus the L norm. Switch the order of the 2 terms, change the sign, integral in time. You can estimate can integrate in time, and in the end, the integrate of the L3 norm is bounded by a constant, which means that limit of time of dA is going to 0, but since A is a fixed constant, so also L3 norm will be equal to 0. So this is the end of the critical case. A couple of remarks. A doesn't have value of T. We'll use this in later. And second remark, you can play a similar game with the supercritical case if the NP norm of the supercritical case is small enough. And since you have dependency from initial data, if a data is small enough in the NP norm, then there is global resistance for every time. Indeed, for supercritical case, this is a paper, this is the method taken from the paper of Toscani. For critical case, we already need a solution, initial data, which is close enough to the delta. And as I said, he considered the energy as and the energy to zero in a finite time. So pick alpha such that alpha plus 1 is between K and P. Take this particular B. Here B belonging to LP infinity or the real belonging to LP infinity. Like in the paper, you can we smooth a bit B, and in the end you can also provide the block for LP and LP infinity. Just a bit of work with computation. So take the energy to norm, the second moment of your solution, write the equation for the derivative. In the second derivative gives the first term, the drift. I mean, is the other term is from particularly the choice of B. And here use a lemma that I will show you in the next slide to estimate the negative term with the mass and the energy divided by the certain power of the energy. So if you allow me to use this lemma, in the end you will have again a differential equality for E such and if you write f of E, you realize that the slope of E go to minus infinity, the more is converging to zero. So in the end, there is a time t such that the energy go to zero. So all the mass is concentrating in the origin at the blow. So the lemma is the following. You can estimate the mass, which is the element norm of F, with the first term, the term I wrote before, and the second power of the energy. Yeah, there is a classical trick for interpolation theory. Take the integral of F, split into terms, where X is smaller than R and bigger than R to be chosen. The first term, you can use Galiano-Nirenberg, you will have the term you want, plus the power of R. The second term is bounded by 1 over R square and the energy. Take R such that these two terms are equal, and then you have your lemma. So this is the easy idea for this lemma. Okay, in the paper, together with Stefano, we also studied the long behavior resolution with a bit more regularity of B. So B here doesn't depend on T, but for long behavior, you need that LP estimate on LP. Otherwise, of course, you can increase step by step to B such that to have a let's say a solution which doesn't decay the Limit equation. This is the aim of this section. So for supercritical case, there are sample of steady solution, so you don't have decay. For critical case and supercritical case, you need that the LP norm is bounded. Your solution again has the heat equation. So I give you an idea just for the critical case. So we have seen that the infinity norm, the integral in time, while the infinity norm is bounded by a constant. So you can pick a certain time, which is bounded, somehow in a certain constant. Yes, sees the constant of the equation, such that at that time the infinity norm is bounded by a divided by 2. Okay, then take the original solution, and by rescaling, you notice that the infinity norm is bounded by a constant a divided by square root of t, where a, I remind you that doesn't depend on t. So yeah, you can play this equation with every t, and a is universal. So we have seen before for a subcritical case that the infinity norm is bounded by initial data and the L2 norm for every interval. So take t0 equal to your rescale time. Take t equal to capital T. And you can estimate for every capital T the L infinity norm as the L infinity norm at time t0 and the so-called interval of the L2 norm square. From the point 1, the first term is bounded by a over square root of t. From the computation we've seen for critical case, the second term again is bounded by the same cost, the same way. So in the end, since a doesn't depend on t, this provides the estimate and the solution in the case of the heat equation for the critical case. So I told you that there is a way to generalize the problem is in a multi-dimensional case. For the method we've seen for subcritical case and supercritical case are working again pretty well. Also for multi-dimensional case, here the critic p is different. Is 1 over p minus 1 over d minus 1 over p, where d is the dimension, or 2 over d minus 1 over p. So we don't know what is happening at critic p, but we have a guess. The guess is there is global existence. And now when you somehow convince you of the guess by providing you analogy with another problem, which is a problem. Yeah, this is not a observation law, this is indeed a reaction diffusion equation. But somehow there is an analogy. Indeed, for this kind of equation, for complete equation, we prove that for subcritical case and critical case, there is only one behavior in the solution, which is block. In our problem for subcritical case, there is only one solution, only one behavior in the solution of global existence. So we guess that, and also in supercritical case, depending on the initial data, you can have either blow up or if you have small data, global existence for beta, and also for our problem, as we've seen. So we guess that also in the critical case, there is only one behavior, which is eventually the global existence, but we are not sure about. So this is the bibliography of the 3 papers I will talk about, and I thank you for the attention.
Thank you, Giacomo, for the wonderful talk. Other questions?
Yes.
Does it make sense to study blow up other norms instead of the other things?
I mean, for our problem, as I said before, you can for this kind of question, you can wonder if there is a block in LP norm. And again, there is a block. You can think there is an intermediate question. I don't know if it's equivalent or not. You can wonder when the solution is there is equi-integrability. So maybe does it converge? I mean, I think it's again, I think it's equivalent to our problem, but maybe it's different. So you don't convert to a delta, but still there is a block. Yeah, but if you in the end, if you have finite mass, I mean, you can have something like logarithm, like the classic example of so the value. So you have a finite mass, but the solution is an infinity. But yeah, I think you can work with this. Yeah, it makes sense actually. Makes sense to wonder a block for other cases. I think there should be something weaker than you know, maybe will be bigger than one. Yes.
Maybe what about the uniqueness of the solution? Is this
Solution is unique. Is unique for I mean, we define the contraction.
okay?
So you're already picking
This class is
the class, but there are also comparison principles. So yeah, for instance, in the first paper, they also wrote you can work with but in their case is B is Lipschitz. So you have higher regularity, and you also have the theory of other theory to provide uniqueness. Viscosity solution. But in our case, it makes sense to work with the viscosity solution for. In any case, yes, you have an interest.
You said that the issue you have in bringing same to the multidimensional cases that you use are Gaussian kind of argument where you need to estimate an infinity norm with the L2 norm of the derivative.
That's right.
Where does the L2 norm, precisely L2 norm of the derivative come from? Is that related to the choice of M that you do at the start of the iteration argument?
No, you can start by, you can just estimate the L2 norm. Here, the L2 norm is just to make, you mean here instead of estimate the L2 norm?
No, just in the where is the suburban embedding?
Here.
Where you have the two norm of the, yes, here, the line above.
Yes, this is the, yes.
The L2 norm of the derivative that has to bound the infinity norm.
Yes, right.
Why you have precisely the L2 norm of the derivative, where does the 2 come from? Where it is related to?
I mean, if you, let's start from here, for instance. Here. If you take n equal to 1, okay, you plug in the equation and then integrate by part, you will have this term. So for n equal to 1, you have the derivative.
Okay, so you can't really hope to estimate another norm of it's really right as the square that appears integrated by parts.
No, because like no, I don't think so, because like you can also estimate the L2 norm instead of L2 norm, doesn't change anything. But then you will appear with this weird guy, and what they do in the first paper is consider if you want replies UN with W. And then applying Gaussian with W. So in the end, you come up also always to estimate the derivative because of the shape. In the end, because of the shape of the operator. Yeah. I mean, I can tell you that something you can maybe an idea that one can explore is instead of working with eta, one can find another cutoff argument with another function, such a way that you can achieve this infinite norm. This is I think the one direction that one can explore.
There are no other questions. I would thank again Giacomo for the follow-up.
Thank you.